right, we are ready for Chapter 7, Section 2. Equality of two matrices. Let's look at this first little definition box right up here and see if we can understand what they mean by this notation. A sub ij equals B sub ij for every I and j. Here's what that I and j stuff means. Remember, in a matrix, we call these things going across what? Rows. In a matrix, they're called rows. They may be numbers, they may be variables, but they are a row. And the value, or the values that are going up and down here are called columns. When we identify a matrix, and I'm going to skip down to the next box real quick, we talk about the order of the matrix. And the order is the number of rows by the number of columns. An M by N matrix. M and N, M is the number of rows, N are the number of columns. So this first box, the first example, I have how many rows? M rows by columns. M are rows, N are columns. First number rows. So how many rows do I have in this one up here? 2 rows, and how many columns? 3 columns. So this would be called a 2 by 3 matrix, or the order of the matrix is a 2 by 3. The I and the j are in the same order that we just said the order of the matrix, rows and columns. I stands for the row position, and j stands for the column position. So if I am referring to any value back down here at the -2, which row is that in? The first, row 1. Which column is it in? 2, the second. So that position, if I'm using the letter A because it's matrix A, I would call that -2 the position A sub 12. 1, 2. A sub 12. Row 1, column 2. It simply indicates the position in the matrix where it is found. So if I ask you, identify for me, now this one happened to equal -2 here in our example. Identify for me B sub 23. So you're looking at matrix B. It's Y, Dakota.
Question. What is this matrix of single digits?
Well, the good news is, not only do we not go past single digits, we're not going to get bigger than probably 4 by 4 matrices. But that is a very good question. I have never run across that in a math class. Good question. Which one is?
The very first page. 2,000, 8,000, 7,000. No, we're not talking about that. We're talking about position.
The number of rows. In other words, you have more than 9 rows or more than 9 columns. That's all right. We're all waking up. So what does this statement mean right here? If I have 2 equal matrices, it means all the corresponding entries, the entries, all these things are entries or elements, they are sometimes called, are equal to each other. So right down here, if matrix A equals matrix B, it's only true if every corresponding position is equal. If the -2 is the same thing as the x, in other words, x is going to have to equal -2. If the A is the same thing as 3, A must equal 3. It's not very hard. So equal matrices means that equal position elements are equal to each other. But that notation is important, so now we can read that notation. We know what they are talking about. So definition of addition of 2 matrices. When you add matrices, you simply add the corresponding position entries or elements. So if we are right down here, notice we have a matrix A and a matrix B, and they're asking us to add matrix A and matrix B. Well, then if I am going to add them, maybe it looks like a minus when I did that, doesn't it? If I'm going to add them, I would take 2 plus a 5, and in the first row, first position answer, my 2 plus a 5 ends up equaling 7. Very difficult. Matrix addition, you add the corresponding positions to get your answer. Now, matrix addition is not always defined. Notice matrix C and matrix D, and when they say C plus D, why is it not defined? They're not the same size or the same order. I have an extra column out there with nothing to add to it, and so this is the troublesome group of numbers. We cannot add those two together. So we would say no solution or not defined, cannot do it. Definition of the additive inverse of a matrix. Now let's recall what an additive inverse of numbers mean. If I have the number 3, I want to add the additive inverse to give me an answer of 0. So what's the additive inverse of 3? Negative 3. That is called the additive inverse. It is the opposite sign of the number is all it is. So if we are talking about the additive inverse of matrix A, it's simply the opposite of A, which means I change the sign on every entry, on every element. It's called the additive inverse. Definition of subtraction. How do we subtract? Well, by definition, which we are not going to do, by definition, there is not really subtraction. Subtraction does not exist. We've said this way back in your memory, probably about Algebra 1, if you were here. Maybe another teacher told you that. Really, there's not such a thing as subtraction or division. Instead of subtraction, we add the inverse. Now, as soon as we get through saying that, we're going to go back and do subtraction. But mathematically, that's what the definition is. We don't subtract. I don't take A minus B. I take A plus the inverse of B. Okay, we're not going to fight about it. We're just going to do subtraction. So right down here, when your book says take A minus B, which means the matrix A minus the matrix B, and they say, well, we're going to make it a plus the additive inverse. So they have taken that negative 1 and it becomes a positive 1, and that negative 4 became a positive 4. They changed it all together and added it. Well, you know what? I don't care if you go back here to the beginning and you say 2 minus a negative 1. What's 2 minus a negative 1? 3. 2 plus 1, which is 3, and you get that answer. So when you do it, I am not going to expect you to say plus the additive inverse. But you need to be aware of what the additive inverse is, and that is technically the definition of subtraction. Moving on. Definition of a zero matrix. I'm not sure why we have to define a zero matrix. It's not really very hard to figure out. What is a zero matrix? A matrix of zeros. That's all it has in it. Okay? What happens when you multiply numbers by 0?
0.
It all goes to 0. What do you think is going to happen? You take a matrix and multiply it by its zero matrix.
0.
It all goes to 0. Moving on. Properties of matrix addition. Yeah, those are kind of nice. Commutative property. This is review of math properties. Do you remember what commutative property meant? Again, way back in Algebra 1, it's probably about the first time. Maybe elementary math. I don't know when they start teaching it. It's when you change the orders. You commute. You change the order. When I add matrices, I can change the order. That's what they're illustrating here, and you get the same answer. What is the associative property referring to? Where the parentheses or the grouping symbols or what you are associating together. When you associate, you group. That's how I remember it. The associative property of addition, and we're talking about when we're adding matrices, I can group in a different order and I still will get the same answer. Additive inverse, we already talked about this a little bit. If you take a matrix times its inverse, your answer is 0. That's the definition of what an additive inverse is. When you add a number and its additive inverse, you get 0 out of it. And then the additive identity property, what happens when you add 0 to anything? Oh, it stays. Oh, I said multiplying earlier, didn't I? I kind of jumped ahead. If you take a number and add 0, what happens to it? Stays the same number. All right, that's all we're saying right down there. Fancy words, easy ideas. Scalar multiplication. When we're talking about a scalar, we are talking about a number times a matrix. So we can use the distributive property. Here I have A, in this case. What are they saying? Oh, they're saying they're all matrices. I have 2 matrices in parentheses with a matrix on the outside. I can distribute it. A times B. A times C. Now they did it BA and CA. Or if I have it on the left side, I can distribute over here. So distributive property is going to work. It probably works with scalars. They should have said, oh, they did. Real numbers, A, B, and C. A, B, and C are numbers, are scalars. They're numbers. And associative property is going to work when I have numbers. These are numbers here. So A and B times matrix A. AB times matrix A. You can multiply that B times the matrix, then multiply it by the scalar A, or you can multiply the numbers together and then multiply it by the matrix. All right. Find the sum of two scalar products. They say we are supposed to take 2 times matrix A, and then, well, let me do 2 times matrix A here. And then add 5 times matrix B. So if I go 2 times this matrix A, it means I am going to distribute that 2 times every single entry in here, or every element. Tell me what the first row will be when I multiply by 2. Negative 4, 6, second row. 8, negative 4, third row. 0, 8. Plus, we're going to multiply by 5 on the next one. What's my first row? 40, negative 10, second row. Negative 15, 10, third row. Negative 20, 35. Good deal. Now we have to add these things together, and we add the corresponding ones. So negative 4 and 40 make 36. First row, keep going. Negative 4. Second row, what will we get? Negative 7. 6. Third row. That would be 43. And we have our answer. Is the math too hard yet? Should be very, very easy. Let's talk about multiplication. And we start by multiplication with a row matrix and a column matrix. When they say a row matrix and column matrix, well, a row matrix only has a row, just has one row. And a column matrix just has one column right over here. So notice they have used these A sub 1, A sub 2, etc. B sub 1, B sub 2, etc. So right down here, when I look for the definition of multiplication, A times B, they've laid out matrix A, and here's matrix B. So a reminder of how I multiply matrices. I take the first element times the first element. First thing in the row times the first thing in the row. There it is. Then I will add to it the second thing in the row. I should change colors. Second thing in the row times the second thing in the column. And there it is. And we will continue with that pattern, dot, 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 all the way to the last thing and the last thing. So looking at this example here, if they give us matrix A and matrix B, ask us to take A times B, we're going to go 2 times 1, there it is, plus 3 times 4. So there was 2 times 1, plus 3 times 4, plus 5 times a negative 6, and we do all our math, and it is a matrix, even though it's one number, so that's why it's inside brackets. There's our answer. That same idea for multiplying gets extended when I get larger order matrices. So here we have matrix A, which is a, tell me the order of matrix A. 2 by 3. That's what we mean by the order. What's the order of matrix B? 3 by 2. Now, we'll probably say it in just a minute, but you can only multiply matrices together if these inside numbers match. If the columns in the first is exactly the same value as the rows in the second. And our solution, do you remember the order of the solution? It's going to produce these outside numbers, 2 by 2. So we can tell from the order of the matrix, number one, whether you can multiply, they have to match those inside, and what the solution is going to look like. So when we go to multiply this, I take row times column. So 2 times 1, there it is. Plus, and I keep going on this row and this column, negative 3 times 4, there it is. Plus 0 times 3, right here. And all these together, now I want you to notice, I just took row 1, I'm going to call it X. Row 1 times column 1. So X sub 11. And where did that answer appear? When I did it all, it appeared in row 1, column 1. Where you are multiplying together is where the answer shows up. And then I stay with that first row, and I move to my second column, and I repeat it. First number times first number, 2, 0. I stay in the first row, and I go over to where my second column is. So 2 times my 0 right here. Plus negative 3 times negative 2 right there, plus 0 times 5 right over there. And we do all that, and we get our first row, second column answer. And then we move to the second row. So we need to try one of those out. Here we go. There's what I was just talking about. Those middle numbers must match, must equal if we are going to multiply it, and our solution will be the outside values. That will be the order of the product. So it says find the product of these two matrices. So when you do these problems, here's the amount of work I need to see. We have the original problem. It is a, what's the order of the first one? It is a 3 by 2. What's the order of the second one? 2 by 4. There's some bad jokes. Can I multiply? Yes, because the two numbers in the middle match up. What will be the order of my solution? It's going to be a 3 by 4. So I'm going to do a 3 rows. It's going to be 4 columns, but it's going to take a little while to get all 4 of those columns in. So I'm going to take that first row times this first column, and we're just going to write the solution. I'm going to put it in parentheses, the solution to this first product. What's 2 times 1? 2. And then what's 3 times 1? Negative 3. That will be our first row, first column answer. Stay with the first row and move over. 2 times 2. First number times first number. 2 times 2 is 4. 3 times 0 is 0 plus 0. There's my second column. First row, second column. Now we're going over to, we'll have a third column, then we'll have a fourth column. Have to squeeze it all in. So first row, third column. First number, first number. 2 times negative 2? Negative 4. Second numbers? Plus 9. Now the last column, still the first row. 2 times 3? 6. Last numbers? Negative 12. There's my first row times all the columns. And then I come down to my second row, and I repeat with all my columns. And we are going to get 4 sets of solutions for all 4 of those columns. So negative 3 times 1, we have negative 3. What is it? 1 times negative 1, negative 1. Then I move over. Negative 3 times 2 is negative 6. 1 times 0 plus 0. Third columns, negative 3, negative 2 is 6. 1 times 3 plus 3. Last column, negative 3 times 3, negative 9. 1 times negative 4 is negative 4. And then we go to our final row, and we repeat it back through all the columns. 1 times 1 is 1. Negative 3, negative 1, plus 3. I'm going to make myself all my columns, all 4 of them here in that row. So second column, 1 times 2 is 2. Negative 3 times 0 plus 0. Third column, 1 times negative 2 is negative 2. Negative 3 times 3 is negative 9. Last column, 1 times 3 is 3. Negative 3 times negative 4 is a positive 12 squeezed in there. And so my final answer, go ahead and read me the first row doing the math. I'll do the first one for you. It's negative 1. 4, 5, negative 6. Second row. Negative 4, negative 6, 9. That's a negative 4. Negative 13. Last row. 4, 12, negative 11, negative 2, negative 9. That's a 12 out there, so it would be? Two plus 0 is called 2. Now is it right? Okay. I'm not going to take the time to go through this next one. You get the idea of how it works. Does it work, though, I should ask? Can you multiply these two? Yeah, it's a 3 by 3 times a 3 by 3. Your answer is going to be a 3 by 3. We call those square matrices. Any idea why? Same number of rows and columns. They're square. That's why we call them square matrices. So some properties of matrix multiplication. The associative property works, so we can associate them differently. The distributive property works. we can distribute them from the left or the right side. The multiplicative identity property. Let's talk about that for numbers for a minute. 5 times what will stay a 5? What do you have to multiply by? 1. You need to know these terms. So when we throw out multiplicative identity, you say, well, if I'm talking about numbers, the multiplicative identity is 1. It doesn't change what it looks like. I remember it because who am I? What is my identity? I'm myself. I look like myself. I stay myself. That's my identity. So what do I do if I'm multiplying and I stay myself? I multiply by a 1. Well, if I'm dealing with matrices, what does that identity look like? Whether I take the matrix times the identity or the identity times the matrix, whichever way I multiply, it stays the same matrix. Do you notice any pattern? That's the identity. Notice any pattern in that identity?
Yes.
What is that pattern? There's a bunch of 1s. There's a diagonal, or we can say an echelon of 1s. Coming right through here, everything else is 0. The identity always looks like that. We only have identities on square matrices. That's not true. Take that back. We only have something else on square matrices. The identity is going to be an echelon of 1s. If I think we only use square matrices, if I have a 2 by 2 matrix, 1s going down the diagonal, everything else is 0. That's the identity. You get an idea for a 4 by 4, what the identity would look like as well. So let's move on to a system of equations. How can I write them as, if I have a matrix equation right here, a matrix equation, how can I write them as a system of equations? We've been dealing with systems of equations and matrices, and we did augmented matrices earlier where the system was all written in one big matrix. And we just did it a minute ago on that number 40, whatever it was that I helped you with. So what does this matrix equation mean as a system? Well, it means that this row has been multiplied by this column, and it's first row, first column, it equals first row, first column answer. In other words, 2 times x, 2x, plus 3 times y, 3y, plus 1 times z, z, equals the number 0. Or it means 0x, don't need to write it, negative 1y, negative y, 4z plus 4z equals what? Negative 2. And if I take the last row of my only column, I get 5x minus 3y plus 4z equals 8. There is the system of equations that means the same thing as that matrix equation. So we have now learned 2 ways we can write systems of equations. We can write them as a matrix equation, or we can write them as an augmented matrix. That's the one big one. That's all I'm talking about today. We're splitting this section into 2 days. So enjoy a more relaxed, slower pace. You can start working.